Oh, hey, how's it going? I'm Jim, the filter guy, and you're at the Abbey Road Observatory. I'm really excited today because something came in the mail for me. Let's just open it up and see what it is. Right, what do we got in here? Boxes. All right, cut that open. All right, look at that. Ooh, pretty snazzy. Let's take a closer look here, shall we? What is this mysterious object? Lots of goodies in here. Some foam, and oh, look at this cute little thing here. Oh, look at that. That is adorable. That, my friends, is a mini refractor, which is the topic of today's video. I'm going to be talking all about what they are and why I love them so much. Oh, it's so adorable. Look at it. Well, before we get into the video, if you're enjoying these videos that I'm making, why don't you click that like button down below. And if you want to stay up on what the ARO is doing, hit subscribe. All right, let's take a closer look at mini refractors. Welcome to today's video entitled Mini Refractors, or It's Not How Big It Is, It's How You Use It. In this talk, I will introduce you to the idea of the mini refractor and discuss some of their benefits. First, let's clarify what exactly I mean by mini refractor. Generally, I am talking about a telescope with an aperture or diameter of 30 to 50 millimeters, a focal length in the 135 to 250 millimeter range, and a mass in the 300 to 1500 gram range. So we're talking about something that will fit comfortably into your hand. Whoops! How did that picture get there? Ah, that's better. Yes, fits comfortably into your hand like a finder scope. But not just any finder scope. We are talking about a finder scope with high-quality optics, like an ED doublet or an APO triplet. Most of the available offerings even come with a field flattener to help provide nice pinpoint stars right out to the edge of the telescope's field of view. At the moment, there are 8 models of mini refractor available. The first mini refractor to become popular was the William Optics RedCat 51, it being released in early 2019. This high-quality Petzval design has set the standard by which other mini refractors are compared. There are now several versions of this scope available, including the dark gray colored Space Cat and the f3.5 Mini Cat. The first commercially sold mini refractor, however, was the Evo Guide 50 from Skywatcher, it being released in early 2018. It wasn't until early 2021 that the next offering was made available, the TPO Ultrawide 40mm. Due to the closure of Oceanside Photo and Telescope in 2023, the TPO Ultrawide is no longer available under that brand name. It is, however, available from the original OEM, Askar, as the FMA 180. In the last couple years, Askar and its parent company Sharpstar have released a number of different mini refractors, rounding out the list with 30, 40, and 50 millimeter aperture offerings. I once owned the Evo Guide 50 and enjoyed it very much. I presently own the FMA 230 and TPO Ultrawide, and just recently purchased the FMA 135. I very much like these mini refractors, the reason for which I will explain in the rest of this talk. Now, with all this talk of mini telescopes, some of you might be saying, I thought bigger was better. Well, that sort of depends on what it is you are trying to achieve. There are a number of reasons why a bigger telescope may not be better for your application. First off, let's talk about convenience. Remember, the best telescope tends to be the one that you will actually use. Many refractors have a number of things going for them in that department. For one, their small size makes them extremely portable. They can easily be packed in your camping or hiking gear, or in your carry-on luggage if you are traveling abroad. Mini refractors are very versatile. You can use them as a finder scope, a guide scope, or a wide field telescope. Finally, they are easy to use. They all come with a built-in rack and pinion or helical focuser. Their low mass means they are easy to drive using the most basic of mounts, and their large fields of view mean the need for accurate tracking is reduced. So, indeed, these small scopes are convenient. But isn't it at the cost of light-gathering ability? I will begin to answer that question by first asking another. Which of the following two telescopes produce the brightest image? By brightest, I mean if you put the same eyepiece in each scope, or the same camera, which one would produce a brighter image? The first scope is the Canada-France-Hawaii telescope. It has a 3.6 meter aperture primary mirror and a focal length of 13.5 meters. Or the second scope is a Takahashi Epsilon Newtonian reflector with 130 millimeter aperture and 430 millimeters focal length. I will give you a few seconds to think about the answer to my question. The answer is the Takahashi. To understand why this is so, consider, if you will, the light bucket analogy. In this analogy, the size of your telescope aperture is represented by the diameter of the bucket, and photons as drops of rain. Conventional wisdom tells us that if you have a larger bucket, you can collect more raindrops in the same amount of time. But what this analogy ignores is the fact that telescopes only use the light that is gathered within their field of view, and field of view is defined by the scope's focal length. The measure of how efficiently a scope gathers light is called its focal ratio, and is equal to the scope's focal length divided by its aperture. The smaller the focal ratio value, the quicker the scope gathers photons. Now let's return to my earlier question about which scope produces a brighter image. The Canada-France-Hawaii telescope has a focal ratio of 3.75, and the Takahashi has a focal ratio of 3.31. Although these are both fast telescopes, the Takahashi is slightly faster, and is thus able to produce a brighter image, all other things being equal. This is why many refractors work so well. They all have relatively fast focal ratios, and so are able to collect light efficiently. If this concept still seems hard to grasp, keep in mind that the Takahashi here has a much shorter focal length than the CFHT, and is therefore gathering light from a field of view that is 31 times the size of the CFHT's field of view. That leads us to the next discussion point: field of view. Recall that a shorter focal length translates to a larger field of view. This graph illustrates that relationship as plotted for a variety of different camera sensor sizes. The relationship is linear, so if you halve your telescope's focal length, you double the field of view. SCTs and other large reflecting telescopes tend to have focal lengths up in the 1500 and larger millimeters range. Refractors tend to sit more in the 500 to 1500 millimeter range. Mini refractors are in the 135 to 250 millimeter range. Thus, you can expect mini refractors to give you a field of view on the order of 10 times larger than what an SCT or large reflector would give. With such a large field of view, the mount tracking accuracy needed to use these scopes is low, saving you time and/or money on your mount setup. The wide field of view can also provide a completely different perspective on the night sky, putting what you are looking at into context. This is the part that I really enjoy. To show you what I mean, I have brought along 3 examples. The first is an object you can observe in the fall. NGC 7635, the Bubble Nebula, located near the border between Cassiopeia and Cepheus. This view of the Bubble Nebula was captured on my 10-inch Ritchey-Chrétien telescope with a focal reducer added to give a focal length of around 1625 millimeters. At this focal length, the details of the bubble are clearly visible. However, the context is missing. Switch now to the view through my TPO ultrawide. Now, we can see that the Bubble Nebula is not an isolated object, but instead is part of a much larger neighborhood of emission nebulae, interconnected by streamers of cold gas and dust. We can also observe the passage of time in this wider view as it contains open clusters like M52 down here, and the Dormouse cluster, that's this little guy right here. We can see mature star-forming regions such as the Lobster Claw, which is this nebula here, and the Northern Lagoon, which is this smaller, brighter one here. Young star-forming regions are also visible, like the Cave Nebula over here. And finally, particularly dense dark nebulae like LDN 1216 and 1230, which we can see up here and down through here. We can see which someday might also become star-forming regions. My next example is of the Crescent Nebula, catalog designation NGC 6888, which can be found in the middle of Cygnus the Swan. This image was captured using the same 10-inch Ritchey-Chrétien as before, except this time with a monochrome camera, my Malincam DS432M. Intricate details are visible in the nebula at this focal length. However, the non-uniform background surrounding the object is curious. Is it just a weird gradient in my image or something physical? Let's zoom out and see. At a focal length of 230 millimeters, we can see that in fact the Crescent Nebula sits in the midst of a vast area of nebulosity. The brightest portion surrounds the central star in Cygnus, named Satyr or Gamma Cygni, which is located just out of frame in the upper left. This large emission nebula has the designation IC 1318. My final example is another summertime treat. M8, the Lagoon Nebula. I very much enjoy observing this object as it is ripe with layers and layers of detail. Star formation at many different stages can be found when observing the object at a long focal length. Even more fascinating, though, is the view at a wider field of view. As with the Bubble Nebula, here too, with the lagoon, we can now see the nebula in context, part of a much larger construct, of which the Trifid Nebula, up here, and NGC 6559, which is this over here, are both part. With a little imagination, one can visualize the 3D nature of this scene. The dark tendrils of gas and dust sitting between us and the billions of stars lying beyond in our galaxy's central bulge. The nebula appears to me like dewdrops snared in a shadowy spider's web. Many refractors make this new perspective possible, which brings us to the last discussion point: cost. Because of the small size of these scopes, material costs are much lower than for other scopes. Also, there is less technical risk associated with making small-sized, high-quality optics. With these two things in mind, one would expect many refractors to be low cost. For the most part, this is true, with most of the available models coming in under $500 US. The William Optics scopes are priced significantly higher, but they are also more complicated optically, having 4 lens elements for the Petzval design. They also have a number of other features, like fancy focusers, that push their price up closer to the $1,000 range. The 50mm ASCAR scope would seem to be priced to compete directly with the Red Cat, being a couple $100 cheaper. Compared with some other fast F-ratio scopes used for astrophotography, mini refractors are roughly a third of the price. In conclusion, mini refractors are available at an affordable price. They are made using quality optics and are very easy to use. I have greatly enjoyed exploring the night sky with a mini refractor. I'm sure you will have fun with them as well. I do have one beef, however, with the mini refractors that I presently own. They do not come standard with adjustable tube rings, which allow one to correct where the mini refractor is aiming. The Evo Guide 50 is the only offering that comes with proper adjustable tube rings. All the others simply have fixed mountings. This is inconvenient when trying to get the mini refractor lined up with whatever scope it is piggybacked onto. Well, that is it. Thank you for listening. If you have any questions about mini refractors, please feel free to leave a comment below or email me at the address in my channel description. If you enjoyed my video, please click the like button. If you would like to stay up to date with what the ARO is doing, hit the subscribe button. Thank you and cheers.